Thank you for this invitation to contribute to the Bergen Day within the Humboldt Week. I'm going to talk about a Humboldt Legacy, the high altitude elevational limits of vascular plants in Europe, North America, Himalaya, East Africa and the Andes. We're going to consider first of all the geometry of mountains, find out what are the highest vascular plants in Europe, try to address the question that Humboldt himself asked: how do we compare elevational limits in different areas on Earth? We'll compare plant limits, tree limits and close vegetation limits. We ask if the plant limits in East Africa and the Andes are in any way anomalous. We'll have some other points and news from up high and conclude something about Humboldt's legacy and conclusions. Now, the global pattern of land area of mountains in the world, going from 1500 meters right up to the top, is that as we go higher there is less and less area at, say, for example, 2000 meters. There's even less at 3000 meters and 4000 meters. And this is the graph just for the European Alps. So if we were to think of this idealized mountain and the number of plant species against the land area, this is a one-to-one line, and this is the actual number of species. So we see, I'm not very good at this. So we see in fact that there's a close relationship between the number of plant species you find at different elevations and the area of the mountain. And this is borne out with data of ours from Aurland in southern Norway, in Montifron in the Alps, and two mountains in the Himalaya. So basically, as land area is halved, on average we have a decrease in the number of species, and for every 157 meters increase in elevation we lose a certain number of species. This is a series of plots of the number of plant species against elevation for very different mountains in the world, and here number 3, Aurland in Norway, and 4 in the Jotunheim, and we see this pattern of the decreasing number of plant species with increasing elevation. There are exceptions, for example on Mount Kilimanjaro and on Mount Armstrong in New Zealand, but in general we're losing about 40 species for every 100 meters elevation. And Arvid Odland and I looked at this in more detail in Aurland and showed basically that species number decreased by about 30 species per 1 degree decrease in mean July temperature as we went up the mountains. And this is the same in Jotunheim, using some old data of Jurgensen's 1932. A 30 species decrease per 1 degree decrease in mean July temperature. So you might ask, well, what happens when species cease? So if we carry the Jotunheim plot down, we see that at about 2.3 degrees centigrade, there should be no species. It's too cold. In the Canadian Arctic, which of course is not mountainous but large flat areas, there the plant limit is about 1.2 degrees centigrade. So what are the highest vascular plants on Earth? They're all in the Himalaya, as you'd expect. 20 species grow above 6,000 meters. They belong to the Brassicaceae, the Asteraceae, the Caryophyllaceae, the Poaceae, the Primulaceae and the Saxifracaceae. And the champion of all is this member of the composite family, Cerciurea Nephaloides, followed by this Mania himalayensis in the Brassicaceae. In the Himalayas, the highest standard vegetation, 9 species, is about 5,960 meters, and the highest closed sward of vegetation is about 5,500. And when you're in the Himalaya, there's often a very sharp transition. At about 5,500 meters, plants suddenly become much more sparse. So there is, in theory, at least 900 metres potentially available for occupation today, assuming no climate change. So the limiting factors probably include the type of habitat, the presence of soil, nutrients, wind exposure, soil temperatures. So it will vary obviously from mountain to mountain. And Whymper wrote once, these are atoms of life in a world of desolation. Well, very few people have ever tried to study these high-level plants, and the main work has been done in Ladakh in India by a group from the Czech Republic, and they transplanted plants from high elevation to even higher and so on. And 10 years later, they showed that the plant which they had transplanted from 6,300 metres, the things planted up to 6,030 metres survived, but after that they did not. And they suggested this was some physiological constraint, probably due to root temperatures. So, the problem that Humboldt asked, how do we compare the elevational limit in different areas? So this is the elevation of the plants, the highest known plants, the region, and the type of biome or vegetation type they occur in. So the highest in Africa, in the Andes, in the Alps, in the Rockies, and in Norway. So what Humboldt did very brilliantly was to suggest there were consistent vegetation patterns across the world, and obviously in Lapland the forest limit is quite low, in the Alps much higher, in the Pyrenees, and so on. And so he was fascinated by this. He collected enormous numbers of data points on vegetation, temperature, elevation, and proposed there were these elevational bands. And in his famous Cosmos book, he compiled this and tried to understand the patterns. Well, most recently, Christian Kerner in Basel has built on this and shown these are the thermal limits from 60 degrees south to 80 degrees north, that there are 7 main thermal belts in the Earth's mountains, and this dark line is the climatic tree line, which turns out to be consistently at 6.5 degrees centigrade with a growing season of greater than 94 days. And what we're most interested in is the white, the nival zone, the very highest tops, where it's less than 3.5 degrees centigrade and a short growing season. So Kerner constructed this diagram. It's a hypothetical section from 60 degrees south to 80 degrees north, forest, alpine zone, and then this very pale blue is the nival zone. So if we now put on where are the highest plants, obviously Cercium phalloides in the Himalayas is way up there. In Africa, Arabis alpina, which we've seen on Mount Kenya, and then in the Andes, 3 species, some in the tropical parts, some in the subtropical parts, then in the Alps, and then Ranunculus glacialis here in Norway. So we see that the highest plants naturally occur right at the edge in the nival zone or just in the alpine zone. So in 2011, Christian Kerner found what he called the coldest place on Earth with angiosperm plant life. And it was a place near the summit of the Dom, the highest mountain in Switzerland. It was found by climbers, and they took Kerner up there and lowered him down on rope. And here at 4,505 to 4,507 metres is growing Saxifraga opositifolia. The plant is about 30 years old, and it also had a lush assemblage of other species. Kerner put out automatic data loggers and showed that effectively what mattered was that the mean temperature of the growing season at this site was 2.6 degrees centigrade. and so all the plant parts, including the roots, experience temperatures of less than 0 degrees every night. And he also had data loggers out in the Himalaya and on Svalbard, and to everybody's surprise, it turned out that this locality, the Dom in Switzerland, is colder than the sites in the Himalaya or in Svalbard. And his estimate of 2.6 degrees is very close to what Arvid Ordland and I had suggested from the Jotunheim data, that plants stopped between about 2.2 and 2.3 degrees centigrade. So here's Kerr's data logger data. Here's the mean of the warmest month. That's the growing season, 2.8 at the Dom, 4.7 on Svalbard. So the likely limit for plant growth to persist is about 60 to 70 degree day growing season with at least an hour where temperatures are more than 3 degrees or a daily mean greater than 0. We don't know what is the limit for sexual reproduction. That's quite another matter. And of course, the Dom saxifrage may be a result simply of a natural transplant. It's rather a sort of exceptional thing to occur. But once it got established, it was able to persist beyond what you might call the species reproductive range. So there's this critical role of plant establishment and the role of chance in extreme habitats. Now the plant at the Dom, Saxifraga positifolia, is also the highest plant in the North American Rockies on Mount Elbert, and it's also the world's northernmost plant at 84 degrees north in Greenland. So this is the world's northernmost plant and also the plant in the coldest place where angiosperms grow. And in Norway, the highest plant we have is Ranunculus glacialis. This is actually taken in Switzerland, and where it grows up to about 4,275 metres. Now there's 6,400 metre records set by the great climber Eric Shipton of Cercirina phalloides in 1938. He found it, according to his notes, in a big scree below the south-facing cliff on the Tibetan side near the Everest, the East Rongbuk Glacier, close to the North Col, and it's not, as far as I know, ever been refound. He also collected, but it was never identified until recently, an undescribed species in the Brassicaceae, the crucifer family, which has now been called Lepidostemon everestiensis. So presumably, like Saxifraga positifolia on the Dom, the Sausuria is growing in some very specialised microhabitat. And there are no other species known at over 6,400 metres in the Himalaya, but there are 13 that occur above 6,000 metres. A Swiss expedition in 1952 came from the other side. They came from the Nepalese side of Everest, and they found 3 species between 6,350 and 6,355 metres on the cliffs and moraine at the north side of the Khumbu Glacier. And 2 of these were species new to science. And now the Czechoslovakian work have added 5 additional 6,000 plus metre plants in Ladakh. So if we try to compare the highest point of the mountains, the highest point at which plants grow, the tree line, and then the ratio between plant limit and tree limit and plant limit and the highest point, we see that in the Alps and the Rockies, there's a lot more mountain where plants could grow. So the limit between plant life and tree limit is rather great compared with the other places where it's less. So temperate mountains have the largest area between the tree limit and the uppermost plant limit. As regards the upper limit of closed vegetation, here's the upper limit of closed vegetation, upper limit of plants. There's little difference between areas except for East Africa and the Andes, where plants grow higher than the closed vegetation. So this has led to the question, are the plant limits of the Andes and East Africa anomalous? Well, here on Mount Kenya, How do you define the tree limit when these are in fact tree senecio and tall lobelias? The tree limit here would be 4,000 meters if you call these things trees. But if not, then the actual highest trees are about 2,500 meters. So it is anomalous. And the same problem in the Andes with Polylepis, of which there are several species. And this can be up to 3.5 meters tall, up to 4,410 meters in Bolivia. And it forms many outposts amongst boulders beyond what one would call a tree line. Either this is a shelter hypothesis, an unusual habitat, or they're relics. And these might well be related hypotheses, but we don't know. So in 2014, we explored part of southern Peru near the village of Tassa and looked at the gradual transition from grazed grasslands to alpine zone at about 4,000 meters. And the alpine vegetation here in southern Peru consists of two things: large cushions or minute little herbaceous plants, mainly in the genus Nototrichi of the Malvaceae. And we found 12 such Nototrichis, 2 of which were undescribed. So it's a surprisingly rich flora given the elevation, but they're nearly all very small in contrast, for example, to the Himalaya. So these are the cushion plants: Pycnophyllum glomeratum in the Caryophyllaceae, Nioides coarctica in the Asteraceae. And you can see how big, how old this Nioides must be, because all these stones have fallen off its edge. So it's probably at least 100 years old. This is what it looks like. It's a rather desolate sort of place, but you do find some small little plants: a senecio, a draba, Plagobotrytis in the Boraginaceae, and a small Ephedra rupestris. A beautiful member of the Loasaceae, Chiophora rosculata, a small Cerastium, a small Astragalus, a new species of senecio, and 2 other members of the Asteraceae. In slightly damp places, you get sort of wet spots richness, dominated by Distichia muscoides, in which grows a beautiful little gentian, Gentianella luteomarginata, Juncus ebracteatus, and another species of Verneria. Now we come to the mysterious and challenging Nototrichi. It's in the Malvaceae. Frankly, they all look rather similar. There are 4 different species, and some of them are a little bit different. And then these 2 appear to be completely undescribed species. So they are really very, very troublesome. And the other feature is, of course, the big cushions. This is a member of the Apiaceae, Azorella compacta, and with my wife sitting on it, you get an idea of its size. Lower down, one sees one of the most unusual subalpine plants ever, and Humboldt himself noted it, this rather hideous looking trunk. This is a burnt version, and actually the plant is like this. It's 3,700 meters. It's Puya raymondii in the Bromeliaceae. So you can see some of these burnt stumps, and these plants can grow up to 100, 120 years old. And there's my wife standing as a scale object. So this is the most crazy alpine plant to be quite so big, and it has these nasty spines on the edge of the leaves. So it's known as the Queen of the Alps, and in Europe we call Erythricium nanum the King of the Alps. So why do these plant limits in the Andes and in East Africa seem anomalous? Well, firstly, the problem of trying to define the tree line, and hence the bioclimatology. Vast areas are unexplored, and it's very, very difficult to explore them. Extreme climate in terms of cold, drought, wind, cloudiness, etc. And when we're on Mount Kenya, it's summer in the day and it's winter at night. And the taxonomy is very poorly known. Daniel Montanez, who did his PhD, started off being a PhD on Peruvian vegetation, but there were so many taxonomic problems that 65% of his thesis ended up on plant taxonomy. And it's probably not as anomalous as has been suggested. So, what other news would we be telling Humboldt if we could talk to him now? Well, the first thing is the amazing discovery of so-called snow roots in this little Corydalis, conorhiza in the Russian Caucasus. Here is the Caucasus with Rhododendron caucasicum. And this snowbed plant has recently been discovered, it grows around the edges of snowbeds, to have snow roots. So as the snow melts, you find this great mat of very fine-grained roots emerging. And these are in addition to the normal roots that anchor the plant into the soil. So as alpine plant growth is often limited by nitrogen and phosphorus, we know Corydalis gets phosphorus through fungal partners, but what about nitrogen? So a Russian group watered snow with radioactive nitrogen-15 and compared Corydalis with Taraxacum, the dandelion, that has no snow roots. And you can see this is the concentration of nitrogen-15, how much it has got into the Corydalis with its snow roots and not into the other plants. They're different anatomically, they're very, very fine, they can form this dense network, but unfortunately they disappear when the snow melts, and so nobody'd ever noticed them before. And so the obvious question is, what about other snowbed plants? Do they too have snow roots? There was a slightly misleading article recently about the world's highest plant, which was described from the Ladakh region of India at 6,150 metres. So, as we've seen, it's not quite the highest. Eric Shipton's Saussurier at 6,400 winds. And this is a large caryophyllaceous plant, Phycospermum cespitosum, and this group found 8 species, but there again the growing seasons had mean temperatures between 2.7 and 2.9 degrees. So it's not as cold as Kerner's Dom locality, but clearly that's still the coldest place with a plant. Mount Everest now, of course, has been climbed many more times and explored, and we now have 13 species above 6,000 metres, mosses 7,000 metres, lichens to 7,400, and snow algae to 7,700 metres, and bacteria and microfungi to 8,400 metres, but they have probably been carried there by all the tourists who go to climb. So what is very interesting about these very high altitude plants is that they are confined really to a few families or genera, and big cushions are not uncommon, especially in the subtropical mountains, the Apiaceae, the Asteraceae and the Caryophyllaceae. And cushions, those beautiful cushions, they are important in many high nival floras. 54% of the high flora of Everest, 52% of the European Alps, 49% of the Hindu Kush, 46% of the Caucasus have cushions. What is surprising is that although the Saxifraga positifolia in the Alps, in the Dom, in the North American Rockies, in Greenland, has the record for extremeness, there's only one other saxifrage in the very high alpines at all, Saxifraga lignitis var everestiensis. In Norway, on Galhopigan, Saxifraga positifolia gets to 2,350 metres. So recently, in an analysis of the highest vascular plants on Earth, Cedric Denton wrote, "It seems timely to encourage a renewed approach to mountaineering, one which integrates awareness of scientific issues and a culture of data collection. Climate change and its consequences on biodiversity could be an interesting topic point of convergence between mountaineers and scientists. And certainly Shipton, Tillman, Colley, Odell, Wollaston and Zimmerman, they were all great mountaineers, but they'd also had a scientific training. And their finds were a challenge to a new generation of scientifically trained mountaineers interested in our changing world. And Humboldt was primarily a scientist and a polymath, but clearly had to have been a very, very good mountaineer to have got to 5,878 metres on Chimarosa. So his legacy, obviously the great publication in 1807 on the Essay of Geography of Plants, laid the foundation for elevational limits of plants, and he found Draba aretioides at 4,600 metres and made a beautiful, elegant and accurate drawing of it. He distinguished 4 broad elevational zones, tropical, temperate, boreal and arctic, and subdivided these into elevational regions which have some similarity to Kerner's more recent analysis. Other botanical legacies, he discussed the Mediterranean and the Pyrenees as barriers to plant spread, the similarity of species in East Africa and California and Mexico. To understand plant distributions, he said we need fossil evidence, and as a paleobotanist myself, I totally agree with him. Changes in vegetation over long time periods he thought might be due to changes in solar insulation, which we know is now the case. And he looked at the ratios of different families to each other in different regions. Species family, species genus, genus family ratios. And some families are more common near the equators, or the more common near the poles. So the basic message from Humboldt's legacy: so many things are still to be discovered high up above the trees, and the North Face used this logo, never stop exploring. And today there are a huge number of exciting books on alpine botany in different parts of the world, like the Pantapuri, Central Asia, the Hindu Kush. And I'm sure if they'd been there, they would be intensively studied by Humboldt in his most wonderful study. And this painting of his study is my ideal study, if only I had the space at home. Books everywhere, maps. The only thing I would change was I'd make this shelf devoted to CDs of classical music. And mentioning music, my one regret is that we're unable to have as background music the Humboldt Cantata, also known as the Welcome or Greetings Cantata. It was composed specially by Felix Mendelssohn in 1828 for the Natural Scientists Congress in Berlin, with 600 participants, organised by Humboldt and his brother. It's the most curious piece of music: 2 clarinets, 2 trumpets, 2 horns, low strings of cello and bass and timpani, plus a 4-part male choir with 4 soloists. 7 parts, about 25 minutes. It's rarely ever been performed. It was performed in its debut in 1828. It was performed in the Humboldt birthday year last year, but has never ever been recorded. And the text shows a progress of the natural world, as in fact Humboldt saw it, from chaos to unity and the development of the glorious world. And the Lord is asked to bless the strivings of the united force. So I would just like to acknowledge people who've helped me see some of these high elevation plants, or discussed with me my interest in high elevational plants. So thank you for joining us on this International Humboldt Day 2020.